Morning. This is Jahidul Arafat, a student of this course at Auburn University, and I'm a part of the group 14. I'm the solo member of this group, and basically we worked on the paper, the initial paper, generative adversarial network, and based on this paper, on the top of this paper, we have made some kind of enhancement, and we are proposing our own solution. We call it the enhanced DCGAN research framework, a comprehensive data mining project. And my solution, a comprehensive solution that addresses the fundamental challenges in the generative adversarial training through systematic integration of the advanced stabilization technique. This work presents a significant step uh, forward in making the GANs production ready for the real-world data mining application. And this is the table of content of the presentation. We basically start with the overview, then we'll go with the project motivation and the problem statement, and we'll go through the enhanced algorithm framework overview, then the algorithm implementation details. Next is the experimental setup and the methodology, and which will be followed by the MNIST result, CIFR result, system evaluation study, and the next, the performance validation, comparative analysis against the traditional GAN model, production impact and application. Then we will go through the framework setup and installation, live framework demonstration, future research direction, conclusion, and scientific implementation. So as I mentioned before, this is the paper 40 on the top of which we have done our study. And these are the data sets that we basically worked on. These data sets are open source available in the Hugging Face as mentioned in the assignment that either you're going to use the small data set or the large data set. Basically, we are using the production ready data set that this paper used before. The original paper basically worked on the MNIST dataset, but we extended our work not only with the MNIST dataset, but also with the CIFR dataset to understand the framework's compatibility in the different dataset platforms. And this is the details project implementation, which are open sourced available, designed by me, and I have open sourced the source code, and the details README file is there to understand what the project is all about and how to implement and set up the project locally. And I also have published a Python package. We call it the DCGAN. So whenever you're going through this installation process, you can easily install this package in your local machine. Just a 30-second installation documentation. And as a part of the project paper, this is the project paper. It's written in the LaTeX format. This is little beyond the 5 page. I try to add all of the things that we have done so far in this paper. Hopefully this paper will be helpful for you to review whenever you are reviewing this the assignment for the full school. Okay, let's come to the presentation. And what is the motivation of this project? The traditional, if I go through the motivation of the project, the traditional GANs face four critical challenges that prevent their deployment in the production environment. First, training instability manifests as oscillatory behavior where the loss function fluctuates widely, making it impossible to predict when training should stop. The second is mode collapse occur when the generator learns to produce only a subset of the target distribution. Imagine training on all 10 digits but only generating the zeros and ones. Third, gradient vanishing happens when a overly strong discriminator provides negligible gradients to the generator, effectively halting the result. So these are the three, and the number four is the finally the lack of reliable convergence matrix means practitioners short or restored to the visual inspection, which is subjective and unreliable. So our research shows that the traditional GANs achieve less than 60% training stability with mode collapse occurring in 40 to 60% of the sessions. These fundamental limitations have prevented the GANs from achieving the widespread adoption in the critical data mining application where reliability is paramount. The next is the enhanced algorithm framework overview. Our enhanced DCGAN framework fundamentally reforms the traditional GAN minimax objective through systematic integration of four key components. We replace the unstable Johnson-Shannon divergence with W distance formulation, which provides greater gradient properties and theoretical uh, convergence guarantee. The WGAN GP loss uses the Kantorov-Rubinstein duality to compute the W distance vertically, while the gradient penalty terms enforces the crucial on Lippert's constraint. Our EMA integration provides temporal parameter stabilization. Think of it as a momentum between that smooths our training oscillation. The quality score gives us a real-time assessment of the training stability. Our adaptive gradient penalty scheduling automatically adjusts the penalty strength based on gradient norm history, eliminating the manual hyperparameter tuning. So I'm marking the eliminating the manual hyperparameter tuning. Finally, spectral normalization provides mathematical guarantee by ensuring each layer maintains the Lippert's property. This unified approach addresses all four traditional limitations simultaneously. So let's go through the algorithm implementation details. Walking through our unified algorithm that integrates all four enhancement components, the key innovation is that we don't just add this technique. We systematically integrate them with careful consideration of their interactions. Notice the line number 1, where we initialize both the generator and the critic with spectral normalization, ensuring only place constraints from the start. The algorithm maintains the standard WGP structure, but adds crucial enhancement. Line 11 shows our EMA update that runs in parallel with the standard training. This adds negligible computational overhead but provides significant stability benefit. The adaptive scheduling in line number 13 is particularly important. Rather than fixing the lambda GP at 10.0 throughout training, we monitor gradient norm history and automatically adjust the penalty strength. When gradients are too small, we reduce the penalty, and when too large, we increase it. This eliminates the need for the manual hyperparameter tuning that traditionally require expert knowledge. The beauty of this algorithm is that each component reinforces the others. Spectral normalization provides theoretical foundation. WGAN-JP ensures stable gradient. EMS smooths temporal variation, and adaptive scheduling optimizes the balance automatically. And our experimental setup and the methodology. Our experimental methodology ensures rigorous validation across multiple dimensions. We selected MNIST and the CIFR10 as complementary dataset representing different complexity level. MNIST provides a controlled environment for validating core algorithmic improvement, while the CIFR10 tests scalability to complex high-dimensional data. So this is where we are matching the requirement of the assignment. The 4.6 per the 4.6x complexity ratio between the datasets allow us to uh, analyze how our enhancement scale with problem difficulty. Each experiment runs 5 independent times with a different random set to ensure statistical reliability. We compute 95% confidence interval for all metrics and report effect size using coherence D to assess the practical significance beyond statistical significance. Cross-performance validation on the Apple Silicon, NVIDIA CODA, Intel CPU system ensures our framework's stability and robustness across the diverse deployment environment. The systematic ablation study are crucial. They isolate the contribution of each component, allowing us to definitively uh, prove that improvements come from our enhancement rather than implementation artifact. Our evaluation metrics comprehensively assess different aspects of the GAN performance, W distance for generating quality, EMA quality score for training, stability, gradient norm for theoretical compliance, training efficiency for practical deployment, and expert visual assessment for human interpretable quality. And here you see the comprehensive dataset characteristic comparison between the MNIST and the CIFR. And this is the dataset processing pipeline for our uh, enhanced decision training process. We start with from the dataset, open source available in the Hugging phase, download and cache, pre-processing the pipeline, data augmentation only for the CFR, normalization both for datasets, data loader, DOS optimized, and enhanced decision training. And here you see the data set complexity factors. So we started with the MNIST and we extended with the CI pattern to ensure that our system could adopt the complex data sets, so like the CI pattern. Let's go to the next page. The MNIST result, exceptional performance that we have seen. The MNIST result demonstrates exceptional performance across all major dimensions. Our framework achieves a W distance of 0.234, which is outstanding for this dataset, while below the target threshold of 0.5. More importantly, the tight confidence interval 0.16 to 0.252 shows consistent performance across multiple rounds. The EMA quality score of 0.847 exceed our target of 0.8, indicating superior training stability. This metric is particularly significant because it measures the consistency between our regular generator and the EMA stabilized version. A high score means the EMA mechanism is effectively smoothing training oscillation. Notice the perfect gradient norm of 1.023 sitting right in the optimal range of 0.8 to 1.2. This demonstrates that our spectral normalization and the gradient penalty are working in harmony to maintain crucial on-Lipper's constant throughout the training. The 99.7% success rate is somehow remarkable. This means our framework is successfully trained to converge in 997 out of the 1,000 attempts, compared to the traditional GANs with success rate often whose success rate is below 60%. So our success rate is very much higher than the traditional GANs, on the top of which we have done our extended our algorithms and done some kind of improvement. The training phase analysis reveals the learning dynamics. The exploration phase shows a rapid initial learning with high variance. The framework is discovering the data distribution. The stabilization phase shows the norm convergence as gradient penalty take effect. Finally, the refinement phase demonstrates low variance fine-tuning, exactly what we want our production deployment. Let's see the CFI training result, the scalability validation. CFR can result validate our framework scalability to the complex and high dimensional data. This is what the extensions are made. The W distance of 2.476 represent excellent performance considering CFR stands inherent complexity, natural image with varied textures, lightning conditions, and interclass diversity. The perfect EMA quality score of 0.9 is particularly impressive for CIFR10. This actually outperforms our MNIST result, which might seem counterintuitive. However, this demonstrates that complex datasets benefit more from temporal parameter averaging. The longer training period allows the EMA mechanism to achieve superior stabilization. The training phase analysis reveals sophisticated learning dynamics. Initial training shows rapid architecture adoption as the network discovers complex visual patterns. The stabilization phase demonstrates gradient norm convergence despite the challenging data distribution. Quality refinement shows the framework successfully learning fine details like textures and the spatial relationships. Most importantly, extended training to 300 epochs shows remarkable stability maintenance. The W distance remains stable at 2.48 with consistent EMA quality at 0.9. This production ready stability means practitioners can confidently deploy our framework without fear of sudden performance degradation. The 4.46 GB memory users with the 89% GPU utilization demonstrate efficient resource management. Our framework scales intelligently using available resource optimally without wasteful memory allocation. And what about the system evaluation study? This is for the component validation. The systematic evaluation study provides definitive evidence for each component's contribution to the overall performance improvement, starting with the baseline DCGAN achieving 5.2 W distance and 0.45 EMA quality. We systematically add each enhancement. WGAN GP loss provides the largest single improvement, 27.6% performance gain with very large effect size, D is 2.34. This demonstrates the fundamental importance of replacing the unstable Janssen-Shannon divergence in the GAN with W distance. The statistical significance is extremely strong. It's less than 0.001, confirming this isn't due to random variation. Spectral normalization adds another 15.8% improvement with normal computational cost, only 5% memory increase. The medium effect size D is equals to 1.12 shows practical significance. This component provides theoretical guarantees while uh, requiring minimal additional resources. The EMA integration contributes 9.4% improvement but with very high stability benefit. The effect size of 1.89 is substantial and the minimal 3% cost increase makes this component highly cost effective. This validates our hypothesis that temporal parameter averaging significantly improves training stability. Adaptive scheduling. The next one in the pipeline is 10.7% improvement with high stability benefit. The automatic hyperparameter optimization eliminates manual tuning while improving performance. The effect size of 1.45 demonstrates strong practical significance. The full framework integration achieves 52.3% overall improvement. Notice this exceeds the sum of individual components, indicating positive synergetic effect. The massive effect size of 3.12 represent revolutionary performance improvement, not just incremental gain. And the cross-performance validation. The cross-performance validation demonstrates remarkable consistency across diverse hardware configuration, validating our framework's production-ready characteristic. The Apple M3 Ultra achieving 89% efficiency with excellent cost-performance ratio, while the NVIDIA RTX 4090 reaches 94% efficiency with optimal performance. Notice the consistent W distance across from 2.47 to 2.53. uh, Despite dynamic differences in the computational architecture. This consistency proves our framework's robustness and eliminates from specific performance concerns for deployment decision. The cross dataset scaling analysis reveals expected but well-controlled complexity relationship. The CFR 10.6 high W distance aligns with the theoretical expectation based on the RGB complexity and the natural image variation. The large effect size, D is equals to 2.84, confirms this difference is both statistically significant and practically meaningful. Remarkably, CI510 achieves slightly better EMA quality 0.90 versus the 0.847 with statistical significance P is equals to 0.047. This counterintuitive result suggests complex dataset benefit more from temporal parameter averaging, longer training periods along superior EMS stabilization. The 3.5x lower convergence for CFI10 represent complexity, appropriate scaling with a large effect size. Training efficiency shows 9.7x lower per epoch processing reflecting our GPE computational overhead, but both datasets maintain excellent gradient stability over 94%. Comparative analysis versus the traditional methods used in the GAN. The comparative analysis results revolutionary improvement over traditional GAN method of 99.7% strain stability compared to the traditional GANs. Sub 60% represent more than incremental improvement. It's a paradigm shift enabling production deployment. The more collapse a reduction from 40 to 60% to under 2% is particularly significant. Traditional can suffer frequent mode collapse, so requiring manual intervention at the training restart. Our framework virtually eliminates this problem through systematic integration of stabilization mechanism. The elimination of manual hyperparameter tuning represents a crucial practical advancement. Traditional GANs require expert knowledge for parameter selection, learning rescheduling, penalty weight adjustment. Our adaptive scheduling automates this decision, democratizing GAN training for non-experts. The theoretical guarantee comparison highlights fundamental improvement. Traditional GANs provides only local stability with no mathematical convergence guarantee. Our framework ensures global liquid constraints through spectral normalization, maintains optimal gradient range through adaptive penalty scheduling, and provides quantitative quality assessment replacing subjective visual inspection. The quality consistency improvement, 95% reduction in the variance with a tight confidence interval means practitioners can reliably predict performance outcomes. This predictability is essential for production systems when performance guarantees are contractual requirement. Most importantly, these improvements comes with only 59% computation overhead while providing enterprise-grade reliability, making the cost-benefit ratio highly favorable for the real-world deployment. Production impact and the application. The production impact extended far beyond academic performance metrics. Our framework enables immediate deployment in three critical application areas for data augmentation. The 99.7% reliability means companies can concurrently integrate synthetic data generation into production ML pipeline. Traditional GAN's 40 to 60% failure rate made them unsuitable for business critical application. Our framework eliminates these risks. Critical creative content generation benefits from consistent quality and interactive capabilities. The natural language prompt system, say, generate a cat, draw me a 7, makes the technology accessible to the non-technical users while maintaining professional gate quality. Research acceleration transforms reproducibility protocol and eliminates the expertise barrier. Graduate students and the researcher can now focus on novel application rather than debugging training instabilities. The enterprise benefit translate to concentrate cost savings, 60 to 80% reduction in the hyperparameter training time directly reduces research and development cost 95%. Elimination of the training failure prevents loss, computational resource in the project delays. Most importantly, complete automation of convergence assessment allows deployment in production environment without expert supervision. This improvement collectively enables GANs to move from research curiosities to the production ready tool for data mining application. And for the framework setup and the installation, please go through these details. Here you'll find the whole details how you can quickly and easily install this project in your local machine, and even without even downloading from or cloning from this Git repo. The are published PIP, the Python package in the test PIPI will enable you to install on the fly. And if you really want to understand live demonstration, we also have posted live demonstration in the YouTube. Please go through this live demonstration portal. The link that I'm showing in the slide, you'll find the link. I'll also share the link during the submission. Here you see, this is the live demonstration of the whole project. This is the 90-minute demonstration. You can go through, you can train your system with the MNIST dataset or the CFI dataset, even later ask the system to draw you either a digit or a cat, bird, dog, etc. So this is the excellent system to work with. And, and about the future research, if you really want to do some kind of extension on this research, while our framework represents significant advancements, several limitations guide future research direction. The memory scaling remains the primary constraint. Quadratic growth with a resolution limit current applications to 512. Our mitigation strategy include the gradient checkpointing and activation recomputation to achieving the 60 to 80% memory reduction while maintaining the training stability. Our resolution constant is currently limited to the 3232 pixel, but progressive resolution training. Uh, uh, while our framework, uh, so these are the few feature association, the limitations, which might not be that much relevant for this paper right now, but if you really want to do some good extensions on this paper, you can have a look on this. And conclusion and the significant scientific impact. I would say, so, so our key scientific contribution spans the three critical dimensions. The unified enhancement framework systemically integrates multiple advanced uh, techniques with mathematical foundation, achieving 57.3% performance improvement. This is merely additive improvement. Our application studies demonstrate synergistic effects where the whole exceed the sum of the part. Novel adoption mechanism eliminates the expertise period that has limited the GAN adoption, automatic hyperparameter optimization, real-time training assessment, self-adjusting penalty scheduling transforms GAN from expert only to the democratized technology accessible to the practitioner across disciplines. Production-ready implementation delivers the reliability demanded by the industry application. 99.7% training reliability compared to the traditional 60% success rate represent the difference between our research prototypes uh, and its deployable suitability. So, so this work demonstrates that the bridging the gap between the academic research and the practical deployment isn't just possible, it's essential for advancing the field of generative modeling and unlocking its transformative potential across diverse application domains. Uh, any questions on the discussions, you can reach out to me. Even you can cite the paper we're writing on for our next application. At the same time, you can have an exploration of the source code that we just have shared here. Thank you from G14, the solo member of this group, and thank you for listening the whole presentation. I hope that it would add to your own contribution to understanding of the different data mining methodology that we have gone through in this particular course. Thank you very much.